Okay, well that's opening to a sound check. I'm doing audio on the iPad. How is the sound?
Sounds good, David.
Good.
Yeah, sounds good.
Yep. There it goes. Tonight's topic, kind of in a similar vein to the software radio digital signal processing presentation last time, is now FT8. And really kind of an overview and picking out the particularly cool things to explain how it works. Or, you know, this is really state-of-the-art stuff, and it truly is. You know, the other subtitle could have, you know, will be at the end, is this cool or what? All the guys that did this really did a good job. So pretty much the same as my last presentation. Just added a few more pictures of building things in my shop. Very briefly, for those of you that weren't at the last presentation, I was, speaking of 68, I was actually 69 as a novice back in Michigan, so an 8 also originally. All my education and professional career is in communications, satellites. Dissertation and the like was on emphasis on spread spectrum. And I, a couple of years ago, retired from SSL, which was Space Systems Lorel or Ford Aerospace, as the chief architect of US government systems, and worked on a number of satellite systems and digital signal processing. And in fact, is appropriate for FT8. In some of those systems, as system architect, it was end-to-end, not just the satellite hardware, but the operations, the network, the user terminals, how everything worked to fulfill particular national security missions. So I was able to work on a number of waveform developments. Some of them able to contribute to, others, you know, benefited and built systems around other people's waveforms. And that preface is really to emphasize what I said a moment ago. The creators of FT8 really did an exceptional job. It is equal in cleverness to anything I had seen in my whole 40 years of professional career when I had a chance to burrow into it. And there's still stuff I want to learn more that I haven't dug down into to really understand yet. So I'd like to start with, you know, giving you some references if you want to burrow further, and do an overview, which will also kind of be definitions. So I'll be able to kind of tell you what I'm going to tell you, and make sure we've got the language established. So as we go through the other topics, you understand. Hopefully I can explain what each of those things are. We'll talk about the user messages, what we actually send, the encoding, error correction, modulation, synchronization, and demodulation. So hopefully you'll get that kind of like what I hope I was able to achieve with the digital signal processing is, oh, that's how it works. And like I said, there's many more cool things that I'm not able to touch on. But you won't be digital communications experts. Like last time, I tried to do only pictures, no mathematics. So we'll see how I succeeded. So I've been talking about this presentation about the same time as the start as the digital signal processing for 9 months or a year. So I was burrowing into trying to get references, and then just so happens in the July and August QEX was exactly what I needed. So Joe Taylor and the guys actually had everything laid out, at least at the top level. And I was actually able to exchange emails with Joe and the guys a couple times. So that was even particularly pleasant pulling this together. So these other references, the QSTs, if you haven't seen them, are very readable. The QEX is likewise readable, but gets into a layer or two deeper than the presentation will. So I recommend all of them. So what we're going to talk about is kind of the end-to-end path here. From when we choose a message to transmit, what the source encoding is, the error correction encoding, and like the digital signal processing, it's kind of fun with numbers. The modulation, the channel, and the demodulation, and even there, the guys have done some very clever things that are very appropriate and really tailored to the HF channel for FT8 and for the other types of modes they've come up with for the other channels like mood bounce, etc., and meteor scatter. On the receive side, we undo all that encoding that we did and process the messages to display to complete our COM channel. So I've tried to keep kind of that overview key in the upper right there. So as a UR here. So the message is the obvious, the human readable messages we send and receive. I.e. the CQs or the calls to people we're trying to communicate with. And that brings up one of the, we'll mention a little bit more, but one of the first enabling things in FT8. As everyone knows, the standard messages are constrained, that we only can send certain things. There's limited use of free text. Other people have defined other modulations, or sorry, other formats that allow you to kind of chat. But the guys actually use that constrained content to increase the efficiency and allow performance enhancing processing. So even their decisions on what messages are sent and the knowledge of what the messages are, they use to make the thing work better. Okay, source encoding, decoding, may sound like a unusual thing, but we're all real familiar with it. So what it is mapping the standard messages into the minimal number of bits needed to enable an increase in transmission efficiency. So Samuel Morse did that too. Use the fewest dots or dashes for the most frequently used symbols. So that guarantees that you send the fewest number of things. So source encoding is a way of simplifying the alphabet to send less bits and still get the information through. Error correction encoding and decoding is one of the more powerful things here, and also the more mathematically intense things. But what it is merely adding extra bits on top of the source encoded message bits that allow very powerful algorithms to detect and correct the transmission errors. So there's obviously a lot of mathematics into what those extra bits are and how they relate to the data we're sending. But for FT8, they've actually chosen one of the most powerful codes there are. And I can probably say, given its level of performance, it's probably as powerful as codes are going to get. Modulation and demodulation we're all familiar with. It's taking those bits and making them into a signal that can be transmitted and received. So that's the selection of the amplitude or frequency or phase transitions or changes that transmit well and can be received and interpreted or demodulated and decoded. So that's the definitions of the things we're going to talk about. So let's kind of work our way through them. And I've couple charts like this one are a little denser than I wanted, but tried to keep the messages pretty on track. So in FT8, what's transmitted is always 77 bits. And the FT8 format assigns specific fields for specific fixed purposes. So again, there's a great structure in what's transmitted to make it very efficient, and also to play some very clever tricks that I'll mention in a bit. For example, standard call signs can be contained in 28 bits. So there's a 28-bit field that's used to send the calls. But for contests or special event stations, there's non-standard call signs, and they allocate up to 11 characters. But that uses some of the 28 bits up. So what the algorithms in WSJT actually do is map the call sign, the standard call sign in that transmission, or in that pair of transmissions, that communications pair, are using a hash code. So they take the 28 bits and map it down to 12 bits and store that within WSJT. But that algorithm to do the hash code isn't unique. Obviously, you lost 16 bits of information, so it can't be unique. But there's good odds that since it's the conversation that's ongoing, your WSJT database knows that call and had that hash code. So most of the time, it's going to decode to a hash that's already in the database. But when it doesn't translate, or it's not in memory, it displays those pointed brackets. So first benefit I had from doing this presentation was, oh, that's what those things are. So it really is symbolizing that it's uncertain of what the received call was because of some of the other powerful games it's playing to send the data it needs. And as I said in the preface, the constrained message fields and the fixed formats are very powerful. So WSJT knows where your call, the other call, and other control fields are located. And if you're in the midst of a QSO, you called someone, WSJT knows it's looking for the guy replying to you. So there's likely known data patterns that it can use. And when we talk about some of the features later, those known patterns in digital communications are very, very powerful things. So the guys use that in the formats and implement it in WSJT. So like I mentioned, there's numerous fields, and they're dependent on the normal use, fox and hound, contesting, this and that other mode. So if you look at the references, there's a long table of potential fields. But they're, they appear, I admit I didn't burrow into them at length, but they appear to be pretty well thought out because they get us most of the features we want to use, again, in those 77 bits. So an example of a clever field is a field they call R2, which is only used to send, the R's, R73, 73, or a blank. So I assume, again, I didn't burrow into the exact encoding, but if there's only 4 messages, R2 only needs to be 2 bits. So there's an example of 4 characters we send all the time that FT8 manages to send back and forth to us with only 2 bits. So that's the example of, the clever mapping of what's needed that the FT8 does in the source encoding. Now, the error correction encoding is one of the most fascinating things. And FT8 uses two state-of-the-art codes to detect and correct the received bit errors. Detection means the algorithm, the mathematics processing can determine, okay, that's not right. There's an error, but if there's too many errors, it can't correct them, so it only can detect it. And with coding, if there's more than that errors, it may actually decode to something wrong. So detection is the mathematics saying, I know something's wrong. And correction is the mathematics can determine what the correct bits are, and what comes out is correct. So FT8 also uses a 14-bit cyclic redundancy check code that's appended to the 77 bits to get 91 bits. The CRC allows calculations that identifies if errors have been received. So those errors that get through the LDPC code, the error correction coding, the CRC flags is nope, there's something wrong. But the powerful part that makes the communication efficiency so high is the other 83 bits that are used to create a 174-bit code word using something called a low density parity check code, or LDPC. And this is one of the most state-of-the-art interesting things that they used. So let's kind of just take a step back and and try to illustrate. Again, it's the mathematics to explain exactly why is pretty tough. But why I just spent a lot of time talking about we did everything we could to send all our messages in 77 bits. The less bits you have to send, the more energy per bit you can expend and the better the communications. So by adding extra bits that are formed in a very peculiar, proper way, those bits we need 97 more bits worth of energy to send from the 91 we already had. So it turns out when you select the bits properly, the algorithms can correct errors and actually end up requiring less energy than just sending more bits. That's referred to as coding gain. So there's the magic in sending extra bits is we can reduce the energy required to communicate. In fact, the LDPC codes are so good that they're near the theoretical minimum. So in 1948, Claude Shannon proved that such codes exist and showed that they could reach what he also defined as channel capacity. And that is the theoretical limit of how many bits can be sent through a channel. We think of it as a radio channel, but it applies to many things. But there's a theoretical limit, just given a bandwidth and an energy, how much information you can send. And it turns out LDPC codes are about a dB or so away from that ideal. And they're not new. They were actually part of Gallagher's thesis in 1960. But they really weren't used until the last few years, maybe 5, 6, 7, 8, 9, 10, that people actually were able to define encoding and particularly decoding algorithms, and computing and processing power advanced enough to actually decode the LDPC codes and achieve that near perfection. So when I started in this business 40 years ago, there was other types of codes, concatenated coding and the like. And we were 2, 3, 4 dB away from theory. And frankly, I never thought you'd get LDPC codes would become computationally efficient and you'd get this good to perfect. So even though I just said I didn't think years ago it would get better, I'll go out on a limb and say, I don't think it's going to get better. You know, a dB is, you know, 25% away from perfection. So, like I said, the mathematics and the computer science needed to define the codes and the algorithms is pretty complex. But hopefully, like I hopefully did with the digital signal processing, I'm going to try to graphically illustrate at a very simple example of why it works. And then I'll kind of challenge you to expand your thinking beyond the little example here, expand beyond 3 dimensions. And you can at least imagine, you know, why big code words and big fancy codes, when properly structured, can get near perfect. So let's look at a 3-1 code, or a repetition code. We'll just use 3 bits to send 1 bit. So there's 8 possible code words. So if you picture them in the 3-dimensional space, each dimension corresponds to a bit position. So there's your 8 code words shown as vectors. And you know, the vector in space is the mental image I wish for you to kind of picture, because in that space, in the mathematics here, there is the concept of distance, which in mathematically is just a difference between the words, and it can be analyzed with other types of mathematics. But distance here means just like we envision it in normal life. So if things are distant from each other, if they're far apart, they're less likely to be confused, or they're easy to tell apart. And that's what this mathematical space is actually doing. So all the fancy finite arithmetic and mathematics is used to define and find codes and algorithms is really just striving to find selections of words, like the 2 red ones we've selected here, to find the selected ones that have good distance properties. So like in our simple example here, you know, if you make 1 bit in error, all the other choices are farther away, the other logical choice is farther away than one of the errors. So if I send 111 and 101 is actually closer, so 000 I can tell apart. So that distance processing, and imagine as the words get bigger and bigger, the processing can get very complex. So that was the reason it took from 1960 onward for people to get algorithms that could go through the gazillions and gazillions of choices and do that in the mathematically correct way that optimized the performance and decoded the received bits in the best possible way. So if you just take the 3 dimensions and picture, you know, very large code words, that's what all this is about. So in that LDPC code used in FT8, the 91 choices are the choices used to send the 91 bits, I should say, are a subset of a much bigger set of words, of bit patterns. And that's the power of the code generation and the algorithms. So the real takeaway here is there's a trade-off of how complex it is and how the performance is. And in fact, even in FT8, the designers chose to use 2 algorithms to trade off speed and accuracy. So within something we use every day is near perfection. LDPC codes approach the theoretical performance limit, and the algorithms that people have derived to decode them perform very, very well and are within the realm of current computers. So of those decoders, their names are the belief propagation algorithm, which is fast and iterative. And FT8 uses that in the first few iterations. It can find most all of the signals using that fast algorithm. The ordered statistics decoding, the OSD algorithm, is a couple dB more sensitive, but computationally more expensive. It takes longer to compute. So everything here has to get done in the 15-second cycle time of FT8. So you see why, again, a clever thing, they kind of get the easy decodes and then use the more complex mathematics to get the other signals. The other thing FT8 uses is something called soft decision data. And I'll mention that when we talk about demodulation. But it's actually, sending kind of digital signal processing like numbers, not just ones and zeros. So it can do even more calculations because of the other statistics and the characteristics of those numbers. So that's what's going on with the encoding and decoding processes. The modulation is very, very cleverly and properly selected for our HF channel for the very dense multi-user environment. So they selected to use 8-tone continuous phase frequency shift keying, CPFSK. The CPFSK is very well selected to minimize the bandwidth. So the continuous phase, and I'll have a crude cartoon of that, but some of us with scope displays on the demodulated waveforms or SDRs, we can actually even see it. When one tone frequency changes to the other, there's no phase jumps. So the mathematics of the frequencies relate that at every zero crossing, everything lines up. So jumps and rapid changes require bandwidth. So no jumps means the signal is contained in a smaller bandwidth. So we can operate, in the 50 hertz on top of each other. There's also pulse shaping, other processing inside the modulation that helps the signal get through a nonlinear amplifier. Again, helps avoiding interference to other users next to us. So FT8 chose a modulation that's tolerant to fading and channel variations, not one that's got the lowest SNR in a constant channel. They could have done a coherent demodulator and done even more mathematics, but for the characteristics of the HF channel and the QSB and for us CW ops, this things we hear like in a polar path, the warbling and fading, that's the things the FT8's got to deal with. There would have been even more bits and more processing, and it wouldn't have probably been a big payoff. So they've chosen a modulation that uses kind of the best compromise for the channel that we deal with. So since it's 8-tone, it's an 8-area modulation. So every symbol carries 3 bits of information. So the 174 bits is actually 58 channel symbols. So again, with the pictures, there's our 8 tones. Frequency axis is vertical, time axis is horizontal. So identifying the 8 tones, they used gray coding, again, to maximize distance. Again, the bits to an adjacent tone are different. So they try to make, again, the modulation have every performance advantage it has. When we transmit, over time, we're sending, you know, tone 1 and then tone 7 and then tone whatever that is, tone 4. And on the right, you can see the continuous phase. So the frequencies and the timing of the waveform is selected, that the differences in frequency between the tones all line up at the end of the period. So you see there's no jumps. The low frequency tone transitions to the next higher frequency tone at the 0 crossing, and it continues. So for a demodulator to determine what the bits are, to get the samples the decoders need to figure it out, it's got to determine the time synchronization. So it's got to know when the bits start and stop, and when the frame or the message, the 15 or the 12.64 second messaging, starts and stops. So FT8 actually puts something called a Costas array in the middle, or sorry, at the beginning, the middle, and the end of the transmission. So there's a known pattern. Remember I mentioned known patterns a while ago that are there, bringing our total of 58 symbols to 79 that WSJT can look for and find synchronization. Some more pictures. You know, that synchronization is actually, or that looking for, is something called a match filter or a correlation processor. It's one of the, with today's computing power, it's one of the theoretically most powerful communications and digital signal processing approaches. So what's going on is FT8's listening for that synchronization array, and then it'll identify at what time it heard the array and in what frequency offset it heard the array. So if we picture the blue field as the match filter. So the blue is the fixed reference in the ideal time and frequency that WSJT has. So for every offset in time and frequency, so a lot of calculations, WSJT is stepping through these offsets and summing up the energy received. So when they're aligned, like shown on this slide, the red signals we sent are exactly on time and exactly on frequency. All the red energy comes through the mask, and that's the maximum energy. We'll identify that signal as being at that time and that frequency. If we look at other signals received that are off in time and frequency, we can see what happens. So the left is the picture we just looked at. The blue field is that fixed reference. If, like this picture is trying to show, it's fixed in time and frequency. So it's fixed in its up and down location. A signal that arrived in the middle, too high, so it's moved up to the top, and its time is too early, it's off to the left. I've shown one here that only 1 bit of energy, 1/7, gets through. So there's nothing heard at that time and frequency. Likewise, on the right, there's one that's too low and too late. So when FT8 shifts the blue field to overlay at the high frequency in the early time, the energy is going to ring up, and FT8 will know that that guy is at this high frequency and early time. And it records that offset as, hey, there's a guy here at this frequency and this time. So the synchronization is only matched when there's significant energy received, and FT8 steps through all the time offsets and all the frequency offsets and listens for the energy to ring up through that blue filter. And that's how it identifies where all the signals are. So where there's that significant energy, the demodulator passes that energy measurements at that time and frequency offset for all the signals that it heard. It passes the measurements to the decoder. So another cool thing, that's why we can choose our own offset frequency and tolerate so-so timing. Because the FT8 is behind the scenes looking for all of our offsets. All of us that are high and low and early and late, and recording those and passing them on to the decoder. So the messages that correctly decode when those numbers are passed and the algorithms are calculated, they're displayed as received signals. But the current versions of WSJT do multi-pass processing. So, you know, we can't hear all the signals. We're back to the early discussion of antenna envy to others. So when we choose our own frequency and time, and we don't necessarily have accurate time, we may be transmitting on top of someone that we're not hearing. Someone distant from us is going to get a big signal with a little signal underneath. So how does FT8 separate them? So the multi-pass processing is the next really cool thing. The codes that I mentioned, they're near theoretically perfect. So what happens is they're perfectly decoded or they're not decoded at all. Since there's high chance that they're perfectly decoded, there's a nearly perfect or likely perfect copy of the received signal now in the middle of WSJT. So it can regenerate the ideal transmitted signal from the received message data. And that signal, we knew what we received because we stored those samples for decoding. So the reconstructed ideal signal is compared to what we received. And again, one of the cool things in the state-of-the-art processing, so it's able to determine the channel distortions, or theoretically what's called the channel function. So the fading, the phase variations, the warble, it can determine that. Use that knowledge to apply it to all the other signals that the first pass, the first iteration identified. Well, now we have reconstructions of what was transmitted at us and subtracted off from the samples we stored. So we literally can reconstruct the big guys, subtract them off, and what's left is the little signals buried by the big guys. So with the current version of WSJT, you've noticed that there's some signals that pop up right away, and a couple seconds later, there's another batch of signals that show up. That's what this is. So I said that there's a lot of power in the known message fields, the known message structure. You saw the blue filter in that processing curve that said, hey, if we know what it is and we can do a match filter, we can correlate process against what we're looking for. That can even improve performance more. In fact, it's communications theory. It's the ideal processing. So, you know, when I called someone, FT8 knows that if I called them, I'm listening for their return call to me. So it knows 62 of the 77 bits a priori, or in advance, or prior. So it can use the knowledge of those 62 bits and, quote, construct a match filter in the processing that's just not making, you know, the algorithms work. It can aid the algorithms because it knows what it's looking for. So that carefully constructed message structure, the creators actually use that to improve the performance. So a lot of the emphasis here is, besides me going, this is cool, is the level of performance is really state of the art. So in sending out a request for some of our colleagues that I know are comm engineers also, John, KK6YP, asked me a question and challenged me and said, well, how good is it? And I said, well, great idea. I didn't think of including a performance comparison, but I just spent all this time telling you how cool, how much they work to improve performance. So the point here is, how good is it? So, you know, CW in the human brain is pretty good. Did a wiki search and some other searches. Somewhere a 1 to 3-ish dB, Wikipedia article said 1 dB is a real good signal to noise ratio that a good CW op can pick CW out of the noise. So if we use, which we usually do, 250 hertz for CW, a standard measure of communications performance is C over N0, or C over N0. So C is carrier power, signal power. N0 is the noise spectral density. It's, you know, signal to noise ratio, signal power over noise power. Except it's is a density. So it's watts over watts per hertz, or it's, you know, watts hertz. When we set it in dB, 1 dB is 25 dB hertz. So FT8 decoding thresholds and all the cool mathematics and computer analysis and simulation that I used to play with professionally, the FT8 team used to determine, did the computer simulations and analysis to determine exactly the FT8 performance in a number of channels. So they determined that the FT8 decoding thresholds are in the order of you know, minus 20 to minus 18 dB and 2500 hertz. So those SNRs, again, translating to C over N0, so we can compare apples and apples, are 15 to 13 dB hertz. So FT8, all the cool things I've been getting excited about, mean FT8 is 10 to 12 dB better, or as much as 2 S units better than the very best CW operator. So when we look at our displays, you know, in 2500 hertz and say, it's decoding signals that I don't even see in the waterfall. Well, this is why. So all the mathematics just paid off. So the real conclusion here is it really is state of the art. The guys gave the ham community, something that's as good as it gets. They really did their work designing it and selecting it for the channel conditions. And their other modes, besides FT8, are selected for other conditions, like I said, meteor burst or moon bounce, etc. FT8 can pull signals, small signals out from under big signals. That provides us performance and a lot of flexibility of operation. And they even used the structure they did to make the performance even better. So this 10 to 12 dB better than CW is actually one of the things that got me interested in having me start to pursue and build hardware for something else. I think some of our members have done moon bounce, EME. Well, now with a 10 to 12 dB advantage, I'm looking at 70 centimeter moon bounce with 4 Yagis and 250, 300 watts. Where before FT8, 10 dB is 10 times. So, 250 watts would be 2,500 watts. So the decoding power of FT8 or the modes used for moon bounce are so good, it makes radio communications and the radio simpler. So not only do these guys enable HF, they enable all sorts of cool stuff. So that's the summary of FT8, and that's what I hope to give you some insight onto not only kind of how it works, but really honor the guys that built this. They did some really good stuff. And that's it.
Yeah. Wow.
Yeah, I knew there was
Nice
some
job,
amazing
David.
stuff going on, but that's incredible.
Yeah, wow.
It's a hell of a presentation. Beautiful.
Thank you.
Especially that ability of the multiple passes. I was wondering, why am I seeing 2 flashes of the codes? And there it is.
Mhm.
Yeah.
I'm
Like I said,
Say that
I had
again.
only
Why am I
seen
seeing-
these things in some
Passes
very,
codes.
very esoteric,
It's
very
basically-
powerful.
You can sometimes have
special purpose
two on
signals.
top of each other.
So they really did a good
And-
job.
And I had this happen today.
Jim, we're hearing
He
you.
had a weaker signal, and this guy was just sitting right fucking on top of him. And he actually, in FT8, got
Thank you. Okay, now do you have a quick notes on that? Cliff notes on that, David.
Oh, pardon me?
Do you have cliff notes available for that presentation?
Yeah. Since I knew it was presented, there's no notes with the PowerPoint. So, unfortunately, I think Lucas is, me excitingly talking my way through it at great speed is all you're left with. And the PowerPoint.
I think I need a second pass at it. That is amazing. So they're using the same technology with their whisper stuff. That's also theirs, isn't it?
Yeah, I looked into it once. I don't think Whisper uses LDPC. I forget what they do. They may use still the old-fashioned concatenated codes, which means 2 codes put together, and that could be, coupled almost as powerful.
Really nice presentation.
Thank you. Is there any other questions?
Well, I was wondering, Russ, KLY, I think you're on here. You do some EME work. Have you, anything you can comment on about what Dave's talking about here and its effectiveness you've seen? Isn't Russ on here? Maybe he's muted and doesn't know it.
Yeah, I see Russ.
Oh, well.
So I have one question. So getting back to my CW comparison,
Yeah,
if you slowed the code down so that now you still have the same 1 dB threshold, and instead of being in a have a 25 dB per hertz spectral density, suppose you sent the code 10 times slower and you were in a 2.5 dB per hertz spectral density. So now what you've done is you've slowed down the information. You can't send as much over the channel per given time, but you have just come all the way back to the same sort of performance numbers that the FT8 is achieving, right?
yeah, and the early moon bounce did exactly that.
Right, exactly. Very slow speed code.
Yeah. And you know, you could do
Because
that
the
with
number that we used was based on 25 words per minute. So if we dropped it to 2.5 words per minute, we'd kind of be there with the same power and receive noise figure and the antenna gain, etc., and channel.
Yeah, and so in the 40s and 50s, and I don't know how long it continued, maybe through the 70s, that's what the moon bounce guys were doing.
Yep, that's right.
And in fact, you know, even here, I just blanked, JT4, the other HF mode, you know, that's twice as fast. So it, you know, requires, you know, twice the power. And the encoding and the performance is similar. So you can trade exactly what your example said, you know, the amount of data you send or the speed for the amount of energy.
But it's interesting. You're sending 77 characters, is it? And it's taking about 15 seconds to send those. I have to figure out how many words per minute.
Or that was a 2 point, whatever the chart had, 2.6 baud or whatever it was. Yeah.
Right. Right. It's about the same, and it should be.
Yeah. Yeah. So yeah, the theory is the, you know, energy per bit is a theoretical number.
Yep.
So your example, if
says
you know, power times time is energy. So you take more time for given transmit power, you're sending more energy. So if you only need so much energy, you can reduce your power if you take longer to send it.
Yep.
Hey, David?
Yeah.
Given what you know about the internals here, what operational hints do you have for us FT8 operators, aside from keeping your clock synced and transmitting as much in the clear as possible?
My first conclusion was, okay, like I said a couple times, they really thought this through about the channel, the operations, what's going on. It pretty much is done everything for us. But you're right, if you can, you know, if you choose a clear channel, but again, it's clear and at your QTH, remotely, you know, they may be hearing other people, so even, you know, but as I said, the software is taking care of that for us. So keeping your time is going to help. I think it said, you know, with the synchronization, and it's like 2.5 seconds off. It can, you know, still pull a signal out.
Yeah.
But you'll interfere with, you know, other people differently. But yeah, keep yourself aligned. But it takes care of most everything. Per your question, I really can't think of anything that we can be smarter than it.
Bob here again. I hope this isn't too far astray, but this really weak signal effort, I keep thinking about the spacecraft communications, the Jupiter and the wherever. Do you know if any of this kind of algorithm technology is being used in by NASA or whoever's talking to those spacecraft out there? Because they definitely are at the weak end of that signal.
Yeah. In fact, with John, we just talked through all the things. So yeah, I do. You know, as you may recall from my intro there, I've worked in space my entire career. The NASA, the earliest probes used some of the older codes. There were a couple dB worse than LDPC. Remember I mentioned you can transmit slower because then you can accumulate more and more energy per bit because you're taking longer to send the bit.
Right.
So deep space, the early probes send it fractional bits per second. I remember like a tenth of a bit per second. I'm not sure that's a correct number, but really slow. I also mentioned that early on, codes were limited because the algorithms were so complex. To go through and evaluate the distances and make decisions on what it really was received required immense calculations. Well, FT8 is real time. We wait for it and it comes to us. The computers are fast enough. What deep space did, and still does, is you store the samples and you process it not real time. You process it however it takes. Because you don't need that picture from Mars in real time.
Yeah,
So
the spacecraft's going to have a lot less horsepower in computing than the base station.
Well, yeah, and it's only doing the encoding.
Yeah,
so the codes are selected for computationally efficient encoding and powerful but very intensive decoding on the ground. So NASA, you know, it may take hours or, you know, a day to receive all the bits. It may take another day for the computer to crunch. So they solved the problem you asked about by taking time, spending more time on calculations and more complex calculations.
Any insight into what Taylor's done here is going to influence that future communication with spacecraft?
Well, LDP, everything new has switched over to LDPC.
Okay.
A couple of years ago, there was something called turbo codes that maybe there's some systems still in use that are using them, but nothing new. Everything is pretty much gone to this, you know, near theoretically perfect. You'll see processing like this, kind of like my DSP conclusion. You know, it's only now calculating the numbers. So everything is going to start looking more and more like this. Different channels can do different games and modulation, different types of interference. We do games with synchronization loops and modulation, demodulation. But all those themes of calculating the numbers this way is state of the art.
So I was kind of wondering if this FT4, FT8 activity that we've got launched into in the last few years, is that driving future communications, or are we just tagging along with what they've learned and applied it to amateur communications?
The correct answer is very positive, but it may not sound like it. So these guys developed this in parallel with all these state-of-the-art things being developed. So they were there with them, and it was equally advanced. So Joe Taylor didn't drive LDPC or any of these algorithms, but he was using it when everyone else was discovering it and making it work, and, you know, used it in the best way possible like everyone else. So those guys deserve as much credit as everyone else that was inventing waveforms at the same time.
Very good.
So the sensitivity basically increases as the square root of the integration time, just like in moon bounce or anything else.
No, the square root is the propagation loss. No, it's linear with time, because energy is watt seconds, so it's power times time. So, twice the duration is twice the energy. So it goes linear with time.
That's true. Okay.
Wow, the hobby's come a long way from the old ICO 720 and a straight key, let me tell you.
I got a 720 sitting right here with a crystal.
I got a 7125 crystal. I'll come by with my J38.
Okay.
So, Dave, one question here. If we took LDPC and applied that to Whisper, I mean, could we work the world on 50 milliwatts in a rain gutter?
Back to the sensitivity, the C over N zeros. I don't know how Whisper compares. It's close. They made different coding and modulation choices for its use. But all the questions we've talked about, energy, and it's the energy to noise ratio. So it's picking signal noise ratio, picking it out of the noise. Yeah. So this performance is as close, for the channel is as close to theoretically perfect as you can get. Whisper is as close to theoretically perfect for the channel they selected there. So they're not that much better or different. But the best you can get, approaching Shannon's theory, is about 1.5 with implementation losses. I'll say 2 dB EB over N0, or that's related to the C over N0 we talked about. So 0 dB is the energy is equal to the noise density. So what you're just barely 1 or 2 dB above it. That's within a dB or so of Shannon's, of the mathematically, the absolute theoretically perfect. You cannot get any better than, okay, Johns, help me. Was it minus 1.3, minus 1.6 dB, whatever the theoretical number is?
I'm not sure I know.
Yeah, it's something like that. So it's only a couple.
Remember, I'm an analog guy, so.
Yeah.
So I guess, the real question would be if we did the 2-minute turnaround time, right? Because as you know, JT65 came on the scene first, but it didn't really take off because of that transmission turnaround time.
Yeah, and again, that's why it's good for moon bounce. So yeah.
Exactly. So there's that sweet spot. However, if you did a 2-minute transmission time with an FT8, error correction type scheme, I mean, what would that do to that mode? What do you think it would do?
Yeah. So again, I didn't calculate it the other way, but remember I said that this FT8 was chosen because of the fading channel and the interference. It wasn't chosen to be the absolute minimum energy. Because it's non-coherent constant phase FSK, it's probably 8 dB EB over N0, so that the minimal signal it can demodulate is probably 8 dB, 8 or 10, something like that. We just said the best real things now are 1 or 2 dB EB over N0, and theoretical is like minus 1 or 1 something. Mm-hmm. So your question is, we're about 6 dB-ish from the other mode, from FT8, from the perfect ideal. Or that's 1/4 the power.
Okay. So
nothing else can be done, the other modes, or in terms of this energy ratio. You're about 6 dB away from as good as it's going to get. And for the channel we operate in, going to go back to HF and FT8, like I said, the processing would, or the delay would be too extreme. So you really can't get much better than they did. So that 8 or 10 dB for this fading interference channel is good as could be practically implemented. So maybe 60, maybe 1/4 power better than we have now, something like that. We're running out of room between theory, perfect theory, and what people are building today.
So was there any, I don't know how much you've spoken with Joe Taylor, but I heard he's working on some new technology. Have you heard anything?
No, I asked a couple questions about, the decoding algorithms, and they didn't have any references. They were very, almost immediately, the three of them were replying on emails for 2, 3, 4 emails. So there was really just, confirming my assumptions or what I read, or pointing me to references. They were very kindly giving me help. They didn't mention, anything else that's afoot.
Okay. Great presentation, Dave.
Thank you.